Alright, so here's a pretty quick exercise. Basically, if you have the cofinite topology on an infinite set and you take an infinite sequence, then this sequence will converge to every point. So this set isn't really like... It's sort of weird that this would be true, but that's how it is. Okay, so let's prove this. So let x, j, and x be infinite. Okay, so we have an infinite sequence. An infinite sequence of distinct points. Okay, so choose any point x in our space. We want to prove that the sequence converges to this point x. Let U be any neighborhood, open neighborhood of x. Usually when I say neighborhood, I mean open neighborhood. I guess in Folland's definition, it's pretty much the same thing, but you allow more things to be neighborhoods. But usually when you talk about neighborhoods, you use the fact that they're open to your advantage. And so I sort of like to just assume that I'm always dealing with open neighborhoods so that I can skip that extra step of dealing with the interior of the neighborhood in order to get the open set that I'm looking for. Because really that's what I want to work with. I want to work with the open neighborhood. And in order to get that out of a general neighborhood, you need to take the interior. Okay, so let U be any open neighborhood. Then U is F complement, where F is a finite set. So, there must exist some natural number n such that xn is not in F for all n greater than or equal to n. Because the intersection of F with the sequence of xj's must be finite since F is finite. And so this intersection has a largest index j such that xj is an element of F. Because there's only finitely many of them, so you can take a max of the indices. And then you just choose an index bigger than that, and that's your capital N. And of course, if F does not intersect with the sequence at all, then you can choose any capital N. Okay. So xn is not in F for any n greater than or equal to capital N. So this means that xn is in U for all n greater than or equal to n, because it's not in F, and therefore it must be in U. This holds for any open neighborhood U of x. I.e., for any open neighborhood U of x, you can go far along enough in your sequence that all of the remaining elements of the sequence are contained in this neighborhood U. Thus, xn converges to x, and hence xn converges to x for all x in x. And so we see here the reason that this infinite sequence will converge to every point is that you can't really zero in on any points using open sets in this topology. Because typically when you think about convergence in the standard topology, what you think about is you look at a point and you consider smaller and smaller and smaller balls around this point. And as you take the radius to get smaller and smaller, these open sets are in some sense getting closer and closer to this one point. And so in order for a sequence to converge under this, let's say this is some metric space. In order for a sequence to converge in this metric space, then no matter how small of a neighborhood around this point you take, you'll always get you'll always get points in this sequence. You'll always get, beyond some index, the remaining points will be in this neighborhood. And so these points really do zero in on just this particular limit x. However, in this topology, the only way you can get open sets to get closer and closer and closer to being around an open set is by you just have to remove elements one at a time. And this process doesn't really zero in on a particular point because you're just you're making you're reducing your open sets at too slow of a rate because you're just removing particular elements, and you can only remove finitely many elements. So yeah, that's the real issue here. That's why you get this crazy amount of convergence, is because you can't really zero in on any points in this topology because the open sets don't allow you to do that. And yeah, that's all we need to do for this exercise, and so now we're done.